Physicists reveal how gamma rays unlock the secrets of lightning. Have you ever wondered what lightning really hides? This electrifying phenomenon, with its dazzling flashes and mysterious power, has captivated humanity for centuries, intertwining ancient myths with modern scientific inquiry. But here's where it gets controversial. Recent research has revealed that lightning's true nature may be far more complex than we ever imagined. Invisible gamma rays emitted during violent storms could revolutionize our understanding of thunderstorms and electromagnetic phenomena. For ages, lightning has fascinated and frightened us in equal measure, inspiring myths and legends that have spanned cultures and epochs. From Benjamin Franklin's pioneering work in the 18th century to today's cutting-edge research, we've come a long way in understanding this natural spectacle. Yet despite centuries of study, many questions remained unanswered until now. Recently, a team of researchers from Penn State University, led by Victor Pascoe, has peeled back another layer of the mystery surrounding lightning. Their groundbreaking discovery? Lightning is not just a simple electrical discharge, but rather a phenomenon closely linked to terrestrial gamma-ray flashes, TGF. These bursts of intense radiation form. These simulations tested various hypotheses and identified intriguing anomalies, such as TGFs that occur without visible lightning. What causes these gamma bursts without lightning? The research continues, and the answers could revolutionize our understanding of meteorology, storms, and even particle physics. These discoveries have the potential to transform our approach to predicting severe weather events and mitigating the risks associated with lightning. Moreover, this research on atmospheric electrical interactions opens up new avenues for exploring broader scientific themes, such as the design of equipment resistant to electrical discharges. In the end, lightning remains a natural spectacle that still holds many mysteries. But with each new discovery, we peel back another layer of this fascinating phenomenon, revealing the complex dance of energy and matter that occurs in the skies above us. Who would have thought that a simple spark in the sky actually hides a cascade of such intricate events? Let's delve deeper into this electrifying topic and share your thoughts in the comments. Do you agree with these findings, or do you think there's more to the story? Cosmic rays trigger lightning. How outer space sparks storms. Lightning might owe its explosive debut to cosmic visitors from the depths of our galaxy. Could charged particles from distant supernovae really be the secret switch that triggers one of nature's most dramatic shows? Two recent studies present the most detailed, quantitative account yet of how cosmic rays ignite the inaugural spark of a lightning bolt, far above the ground, and perhaps even before the storm itself knows what's about to happen. But here's where it gets controversial. Are lightning's origins more cosmic than we ever imagined? Or are we missing an earthbound piece of the puzzle? Let's demystify how this works. At Penn State, physicist Victor Pascoe and his team blended satellite, aircraft, and ground measurements with a cutting-edge 3D storm model. Imagine a high-energy proton, born from a cosmic ray hurtling through space for millions of years, crashing into our planet's upper atmosphere. This collision doesn't just fizzle out. It kicks off a cascade of fast-moving electrons. These energetic particles ride the tangled electric fields inside a thundercloud, each impact unleashing more electrons. Think of it like a snowball rolling downhill, piling on mass and speed. In quick flashes, the cloud emits bursts of X-rays and gamma rays. Those flashes jolt even more electrons loose. All of this happens in the blink of an eye. Within microseconds, the cloud's balance tips and the stage is set for the full spectacle of lightning. Here's the striking detail. The team's virtual storm doesn't just predict these high-energy pulses, it matches them, in both strength and speed, to actual surges observed milliseconds before lightning strikes in real storms. Pascoe sums it up. Their results offer the most accurate, concrete explanation yet for how lightning truly begins in nature. But is this the final word? Or just the next chapter? And this is the part most people miss. In New Mexico, Xuanmin Shao's group at Los Alamos turned an ultra-sensitive 3D radio locating system, two BIMAP 3D antenna arrays staring 11 kilometers apart, towards summer storms. These arrays tracked thousands of lightning flashes in 3 dimensions, even measuring subtle traces of electric polarity. In nearly every event, they spotted a ghostly, ultra-swift negative pulse making chase behind the familiar positive lightning front. Shao and his team explain the cosmic connection. As cosmic rays smack into the atmosphere, they spawn both electrons and positrons, particles with identical mass but opposite charge. Earth's magnetic field doesn't treat them equally. It bends them into diverging trails, carving conductive corridors through the clouds. Lightning follows these pathways, like a train running the rails laid down by cosmic rays. Instead of only seeing the main positive surge, the team's gear uncovered a barely detectable negative discharge, racing just behind. Should we rethink how we visualize the spark behind every strike? Why should anyone care? These new insights don't just rewrite the science textbooks. The findings could transform real-world lightning prediction, helping us protect planes in flight, ready rockets during launch, and distinguish between random bolts and deliberate bursts, especially in sensitive defense contexts. There's even an open question. How might solar storms or distant cosmic explosions tweak the global rhythm of thunderstorms? This is a hot topic for Earth and space scientists alike, and not everyone will agree on which cosmic factors matter most. So, the next time you hear thunder rumble overhead, ask yourself, is the first spark born in your backyard, or did its journey start millions of kilometers away, hitchhiking on a cosmic messenger streaking through space? Do you buy into this cosmic origin story? Or do you suspect the story isn't settled yet? Let's spark a debate in the comments. What's your take on lightning's true genesis? Scientists reveal how lightning actually starts. The hidden triggers uncovered. Imagine a world where one of nature's most spectacular phenomena, lightning, was shrouded in mystery. Until now, scientists have finally cracked the code on what triggers these electrifying bolts, revealing a fascinating and complex process that unfolds within the tumultuous skies above us. But here's where it gets controversial. Some experts are already questioning the implications of this discovery. For decades, while the mechanics of lightning strikes were well understood, the exact sequence of atmospheric events that sparks them within thunderclouds remained elusive. A breakthrough came courtesy of a team led by Victor Pascoe, a professor of electrical engineering at the Penn State School of Electrical Engineering and Computer Science. Their groundbreaking study, published on July 28 in the Journal of Geophysical Research, offers a detailed explanation of the powerful chain reaction that sets off lightning. The researchers discovered that strong electric fields within thunderclouds accelerate electrons, which then collide with molecules such as nitrogen and oxygen. These collisions produce X-rays and trigger a cascade of additional electrons and high-energy photons, creating the ideal conditions for lightning to form. Our findings provide the first precise quantitative explanation for how lightning initiates in nature, Pascoe explained. This connects the dots between X-rays, electric fields, and the physics of electron avalanches. To validate their theory, the team employed sophisticated mathematical models to simulate the conditions observed in the atmosphere. They found that relativistic energy electrons, which enter the atmosphere from space, multiply in the electric fields of thunderstorms, emitting brief bursts of high-energy photons known as terrestrial gamma-ray flashes. These flashes consist of invisible, naturally occurring bursts of X-rays and accompanying radio emissions. By replicating the conditions observed in the field using our model, we provided a comprehensive explanation for the X-rays and radio emissions present within thunderclouds, Pascoe noted. We demonstrated how electrons accelerated by strong electric fields in thunderclouds produce X-rays upon colliding with air molecules like nitrogen and oxygen, leading to an avalanche of electrons that ultimately initiates lightning. Zaid Pervez, a doctoral student in electrical engineering, played a crucial role in matching the model's predictions with real-world data. He compared the model's output to observations gathered by other research groups, using ground-based sensors, satellites, and high-altitude aircraft. We explained how photoelectric events occur, the conditions needed in thunderclouds to start the electron cascade, and the various radio signals observed in clouds before a lightning strike. Pervez said, to further validate their findings, he also cross-referenced their results with previous studies and his own research on compact intercloud discharges, which typically occur in small, localized areas within thunderclouds. The team's model, called the photoelectric feedback discharge, simulates the physical conditions necessary for lightning formation. The underlying equations are publicly available, allowing other researchers to build upon this work. In addition to explaining lightning initiation, the model clarifies why terrestrial gamma-ray flashes often occur without the usual visible light and radio bursts associated with lightning. In our simulations, the high-energy X-rays generated by relativistic electron avalanches create new seed electrons through the photoelectric effect in the air, rapidly amplifying these avalanches, Pascoe elaborated. This runaway chain reaction can happen in very compact volumes and with varying intensity, sometimes producing detectable X-rays but minimal optical and radio emissions. This explains why gamma-ray flashes can emerge from regions that appear dim and silent to the naked eye and radio detectors. The study, published in 2023, was a collaborative effort involving researchers from multiple institutions, including the University of Orléans, France, École Polytechnique, France, NASA Goddard Space Flight Center, Brno University of Technology, Czech Republic, and the Technical University of Denmark. The research was supported by the US National Science Foundation, the Centre National d'Études Spatiales, CNS, the Institut Universitaire de France, and the Ministry of Defense of the Czech Republic. And this is the part most people miss. Understanding the initiation of lightning not only sheds light on a fundamental natural process, but also has practical applications in weather prediction and safety. What do you think about this discovery? Does it change your perspective on lightning? Or do you believe there's still more to uncover?